Hello everybody, welcome back to ISSC 421. This is Professor Labarge. We're going to be covering part 2 of lab number 1, analyzing protocols with Wireshark. In this part of the lab, we're going to load a file of packet capture that's been previously captured by Wireshark. So what I'd like everybody to do is go ahead and double click on Wireshark if you're not already there and drop that packet capture in there. What we're going to do is we're going to move down to frame 546, and we're going to analyze that. Let's see if we can go a little bit of lag. So 546, we got it right here. Go ahead and click that and highlight it. What you're going to see is in the first column right here, as I mentioned and we just clicked on, this is actually the packet frame number. These numbers appear sequentially and there are 765 frames in this PCAP file. I mean, there could be tens of thousands, if not more, depending on just how big your PCAP file is. So once we click on number 546, we're going to drill into this a little bit. What we're going to do is you're going to go to the frame detail pane, and we're going to click the plus sign to actually look at the frame header. What we want to do is we want to look at the byte size of the wire and the byte size of the bytes, what was captured. So right here we have 175 bytes on the wire and 175 bytes captured. This is really important to note, all right, because a difference between bytes on the wire and bytes captured can actually indicate that not everything is being captured or that partial or malformed packets may be captured, which could lead to incorrect analysis. If there are regularly more bytes on the wire than captured, it's possible that the computer that's running Wireshark is not able to keep up with the actual interface. So there's a lot of information here, but again, this is what we want to check, that the bytes on the wire and the bytes captured actually meet. So go ahead and click out of that, and we're going to move on to the Ethernet 2 section. Go ahead and expand both of these windows. And what we're going to do is we're going to take a look at what has been provided. As I mentioned earlier, Wireshark is a very powerful and robust piece of software. It actually takes a lot of the work out of analyzing packets and presents a wide range of information for us. In this detail layer, Wireshark has already determined a bunch of information for us. For example, it has determined that the frame type is Ethernet 2, that the source is Intel Core hardware, that the destination is IP version 4 multicast, that the type of traffic carried in the next layer is Internet Protocol. I mean, it gives you a lot of information that's great. It does all the work for us. We don't have to figure it out. A couple things I'd like to note. So right here, you're looking at the source MAC address, because you can see source, and then you got the source MAC address. The MAC address is 00:22:FA:IC, etc., right? To the left of the MAC address, Wireshark shows this thing called Intel Core. You see it right here. What this means is Wireshark has interpreted the IEEE assigned manufacturer's unique ID. This information is almost always correct, but it can be manipulated. The first 6 hexadecimal characters of the MAC address, so you got 1, 2, 3, so you got 2, 4, 6, right? Hexadecimal actually represents the OUI. The OUI stands for Organizationally Unique Identifier, and it's what's ran by IEEE, and it denotes that the company that actually manufactured the device on the device's network card. So in this case, we know that this MAC address was made by Intel Core. Or I'm sorry, not the MAC address, but the network interface card was made by Intel company. So you can get a full list of the OUIs by just going to IEEE's website and looking for OUI. So go ahead and minimize this, and now we're going to move on to the Internet Protocol version 4 section. In this section, as I had mentioned previously, there's a lot of things, and a lot of it may look like gibberish, but what we're looking at is for key pieces that are going to help us out trying to answer questions about maybe what's going on the network. So as you know, a variety of packets can exist on any given network. The IPv version will determine how the rest of the packet is interpreted. Almost all modern networks, except for academic and research networks, use IPv version 4 or IPv version 6. A different number can also be faked by malicious software or might mean that a packet has been corrupted. As IPv6 gains in popularity, which it will continue to do, it is increasingly likely that you'll see IPv4 and IPv6 on the same network. Both IPv4 and IPv6 will use the same lower layer protocols such as Ethernet, but may have their own specialized versions of higher layer protocols. So again, what we're seeing here is IPv version 4 being utilized. So that's important to know. So now we're going to close that and go to the user datagram field. The information in the user datagram protocol field confirms that the source port in the capture file is an ephemeral or temporary port on the source computer. We know this because of its numeric range. So when you're seeing this right here, the source port, that source port, given that it's a high number, remember, there's only 65,535 ports. This is 64,072. So we know this is a high number, so we know it's an ephemeral port. We also know this because we should know that the well-known ports that you will see on a network run from 0 to 1023. So those are your well ports such as FTP, SSH, Telnet, HTTP. Those are all protocols that are within that well-known port range and ones that you'll definitely need to know. Taking a look too, we see that the port number 1900 is assigned to SSDP. If you didn't know what SSDP is, it's not a big deal. Probably a lot of acronyms that people aren't too familiar with, but it stands for Simple Service Discovery Protocol. It indicates that SSDP is being queried for the existence of services on that network. The Internet Assigned Numbers Authority, IANA, maintains the official list of service names and port numbers for all services such as TCP, UDP, and SSDOP that run over the transport layer. Again, you can just Google IANA and take a look at all the ports. Google is your friend. So definitely get another window open and start Googling and ensuring that things that you don't really truly understand, some maybe acronyms or anything that you take a look at. Again, this piece was just to give you enough information to move through the lab because you're going to be continuing the same steps for for frame 545. What you're going to do is you're going to see that that the filters are one of the most powerful tools in Wireshark. You got your filter area right up here. They allow a very complex set of criteria to be applied to the captured packets, and only the results are displayed. The rest of the packets are still there, but they're just not included in a filtered analysis, but can be restored very easily. It's also possible to save a filtered view of the packets without the additional packets. Filter expressions may either be built with the filter edit dialog window or typed in directly into the filter field, which is right here. All right. You're definitely going to want to get familiar with that. It's definitely something to take a look at. There's a plethora of different filters that can be used. Again, this is just an introduction. Wireshark is a very complex tool with a lot of features and a lot of stuff going on. If you're not using it all the time, it can be very overwhelming. But again, this is just enough to get your feet wet. You should have enough information to repeat the same steps to look at frame 545 right here and answer the assessment questions. If you have any questions, don't hesitate reaching out. Other than that, signing off.